Hello, and welcome to this topics video where I chose to take a Trig SBAC question. I noticed there was quite a bit of Trig when I helped administer the SBAC test at our school here at Belgrade. So this question is kind of cool because I think it allows a good exploration opportunity that GeoGebra can provide for us. And I'll show you in this video how I use dynamic text. So it changes as things change to help students kind of understand this pretty large trig concept. Okay, so the SBAC question itself says, suppose that there's an angle A such that the cosine of that angle is going to be less than the sine of that angle. And then it says to select all, which is, I find, a much better question than just picking one. Select all the angle measures that are a possible value for the angle A. So what they need to identify, I hope, if they understand how to do this, that for all angles greater than 45 degrees, that sine value is always going to be bigger than that cosine value, right? So, one way we can look at this is if we do, and pictures is how I create a GeoGebra app. It gives me kind of the visual of what I want to create. So when I look at this, I think about a 45-degree angle, right? We drew some right triangle. Doesn't matter how big we go, right? We could do something like this also, as long as it's a right triangle. We can talk about similarity if you want to. Maybe that's already been in the discussions. And so for this video, I'm going to assume similarity has already been discussed. So we have a 45-degree angle. We have some side that's opposite of it, some adjacent side, and some hypotenuse, right, for our right triangle trig. So when we talk about, say, the sine of 45 degrees, it's going to be opposite over hypotenuse, and the cosine of 45 degrees is going to be the adjacent over hypotenuse. But the one thing we know about a 45-45-90 triangle is that it's also a right isosceles triangle. Therefore, O and A, our opposite side and our adjacent side, are going to be the same length. Therefore, the sine and cosine values are going to be the same. And then when we look at an angle, say, bigger than 45 degrees, maybe something like this, right? Now all of a sudden, this angle is bigger than 45. Our opposite is going to be longer than our adjacent. Therefore, this ratio value is actually going to be bigger than this ratio value, right? So angles that are larger than 45 degrees will create a sine value that's bigger than the cosine value of that angle. So our answers then are this one, this one, and this one. Okay, so let's use GeoGebra to kind of illustrate that, be an exploration for students that don't understand that relationship yet. Okay, so here's a blank GeoGebra screen. Now when I do these things, we need to create some kind of right triangle, and we can change an angle within that, right? We're trying to create this picture here. One way, I guess, as I'm thinking about it, we may want a triangle, an angle in a right triangle that we can just move around, like, its orientation if we wanted to drag some points, or we can use an axis, and that's what I'm going to do for this video. I'm going to use an axis here, and let's first of all create maybe an angle. We can go lots of routes, and as I'm talking, I'm kind of thinking, let's go ahead and try a slider. And we haven't used a slider, I don't think, for an angle yet. Maybe we have in these videos. But I'm going to grab my slider tool. I'm just going to place a slider over here. I can change my slider. Instead of just being a number, I can make it an angle, which now goes to the Greek letters. This is now alpha, going from 0 to 360. We don't really want 360 because we're only talking about acute triangles, but I am going to let this be 90 because that could be a good discussion. So now let's change our increment jump to 1. That sounds good to me. Alright, so now we have some slider. It's going to be an angle now from 0 to 90 degrees. Okay, so first things, let's create a vertex point. I'm going to put right here at the origin at 0, 0. And then I'm going to put just some point on the x-axis. Remember too, I've mentioned the colors in GeoGebra. I know that my point that I just put on here missed the x-axis because it's that blue color. Blue is an independent color, meaning it can go anywhere we want to, drag it around, do whatever. So I know that it won't stay confined on the x-axis like I want it to. So I'm just going to get rid of that point, and I'm going to try again. And now we get that purplish color, which purple is good because that tells us it can move, but it's confined to an object, like the x-axis. Okay, so now what we may want to do, let's create some triangle here. Let's first of all make our angle, I guess. So for the right triangle, I'm going to grab my segment tool. Maybe we'll make the segments red and make them a little bit thicker. So here's my first side of my right triangle. So from the vertex, I'm going to open up whatever angle this slider says. So to do that, we can do a couple things. I'm going to grab in my angle toolbox, or the measurement toolbox, we can do an angle with given size. So I'm going to go with this one. So remember, if you don't know how to use a tool, you can hover over it and it tells you select leg point, then vertex, and enter size. So this is my leg point, this is my vertex, and then it asks what size do we want to make, and I'm just going to get rid of my 45 degrees, and I'm going to come over here, and I'm going to, in my symbol box over here, I'm going to grab the alpha symbol. And alpha is already an angle, so I don't think I need the degree symbol. Now, when we talk about counterclockwise, clockwise, since I chose this point, vertex, and I want to go up here, we want the angle to open in a counterclockwise position. So right now I have it at 0 degrees, but now, since I defined it as alpha, notice as I move alpha around, that angle is going to change based off my slider. Cool, so now I'm just going to, let's finish off our right triangle. So here's my point on my x-axis that can move around, right? And all that angle with given size tool does is it rotates that leg point, that first point we pick, by the angle we defined it to. So it's just a rotation. These are going to be equal length. Okay, but that's not the case in our right triangles all the time. So I'm going to grab my perpendicular line tool. I'm going to go perpendicular to the x-axis and go through my point that I have on the x-axis. And then I'm also going to connect this angle to our segment. And to do that, I'm going to use my ray tool. So I'm going to click on the ray tool, starting at the vertex, going through my point. And now we can kind of see that right triangle in there. All right, so now as I move my angle around, notice we're going to get different kind of right triangles. And the cool thing too is we can change the size. So it doesn't matter the size, right? And that's a good investigation for students wherever they're at. Okay, last thing is my third real point of my triangle is this intersection. So I'm going to click on the intersection, make sure it's black. Black means it's confined. It's restricted to one point. The intersection is only one point, so that's where we want it. Now I'm done with this little guide point, is what I call it. So you can either right-click on it and go to show object, and we can hide it that way, or just knowing that it's a transformation, it's B prime, I can click on that little green circle in my algebra window also. Okay, and then the last thing is I don't really want this whole line and I don't want this whole ray. I just want that point. So I'm going to hide my ray and I'm going to hide my line. And now I'm going to grab my segment tool and make my right triangle. And maybe for aesthetic reasons, I'm going to show that this is 90 degrees also. So there's our right triangle. Here's an angle, right? So now what we want to do is figure out our cosine and sine values. So let's assume prior to this, students already know their trig ratios. So if we do sine, and maybe what we can do too, is let's show the length of these segments. They're already over here in the algebra window, so students can take a look at the algebra, but because I don't have labels over here, we don't really know. I mean, we can determine the hypotenuse will be the longest, right? But I don't want to guess on what side is what. So I'm going to go over here back to my angle tool, which is known as our measurement toolbox also. I'm going to grab the distance or length tool, and I'm just going to click on my 3 segments. And it's just going to give me those lengths. Okay, so now not only can students hopefully identify opposite, adjacent, and hypotenuse based off of our vertex angle here, but now let's look at the ratios. So I'm going to grab my text tool, and we're going to do some dynamic text here. So what we're going to say is the sine of our angle, it's not labeled, maybe we'll call it A, since the problem calls it A. So the sine of A, which maybe we want to say is equal to, I'm going to click on the text box here. So notice the preview here. LaTeX makes it changes the font a little bit, and then we can do some objects too, or some symbols, I believe. And as I'm thinking out loud, maybe I'm thinking of something else in Microsoft Word. I want to create a fraction. So what we can probably do, if we want it to be vertical, I'm trying to think, if I were to do a fraction, I'd have to use the division bar, which is that kind of weird slant. I want to keep my fraction like the way that we see it, or the ratio the way that we see it, and keep it vertical. So what I'm going to do is say sine of A is equal to, and sorry guys, I didn't actually make this prior to, I'm thinking out loud as I'm talking. It's going to be equal to, and I'm going to create our little division bar. And I hope it doesn't look dotted. It does look dotted like that. I don't like that. Maybe something like this. Oh, it doesn't like that at all. Actually, in the LaTeX formula, if you hit this little down arrow, we can see that we have roots and fractions. So I can click on this A over B. Now in our preview window, even though the LaTeX has some weird notation, I guess. So I don't really know exactly how to use the notation, but I know that it gives us what we want. So my first fraction isn't going to be A. I want it to be opposite. So that this is our sine ratio, which then equals, right? And let's actually show the ratio and the values of our numbers. So what I want to do again is grab another fraction symbol. And again, for A, instead of A, I'm going to go over here and click on the opposite side, which is the 1.84. That's this. So I'm going to click on E. And when I click on the actual variable with the value on the algebra window, notice it creates this little formula box in our text, and in our preview it's showing us the actual value. So that's pretty cool. So the opposite side is 1.84. The B, I'm going to go ahead and make it my hypotenuse, 3.92. So now we can see that the sine of our angle is equal to the opposite over hypotenuse, which I can't spell hypotenuse. Okay, it's going to be equal to this fraction here, which then I'm going to go ahead and say equal to, and we want to actually figure out what this value is. Okay, so now what I'm going to do is actually click on my E again, but in my text box, I'm actually going to take my cursor and click in my text box, and I'm going to say, let's take E and let's divide it by D. So I can click on D, or because I'm in my text box, if I hit D right now, it knows that it's going to take whatever E is and divide it by what D is. So here is, I'm going to click OK. Here's our text we just created. Maybe I'll make it a little bit bigger and bold it and make it green. So here's my nice dynamic text. Tells us what the sine ratio is, tells us what the values are, and what the sine ratio itself is. So now as we're changing our angle, maybe instead of A, I'm going to come back here, get rid of A, and I'm going to say click on my alpha, that is my angle, and now it actually tells us the sine of the angle. So that's kind of neat too. So now we can see the sine value. So the last thing is we're going to take this whole thing here and we're just going to do another one for cosine. So I'm just going to say, I'm going to click on the text, and then I'm going to say the cosine of my angle A, so there's our cosine of 45 degrees, is equal to, on the LaTeX formula, I'm going to go down here to roots and fractions, grab my fraction. A now is going to be the adjacent. B is the hypotenuse. So now in my preview window, we have adjacent over hypotenuse, and I could spell right this time. It's going to equal, let's go ahead and put those values for our adjacent and our hypotenuse. So I'm going to grab that fraction function again. My adjacent side is this 3 point, oop, we're at a 45 degree angle. That doesn't help me. I'm just going to change my angle. Okay. So now I'll go back to my thing here. I'm going to change my A to be what the adjacent side, 3.46, that is actually A. And then my B, which is my hypotenuse, that is my side 4, or D. So now I have, oops, actually have to click on the variable if I want the value of it. Okay, so now we have our value shown, which is also equal to, let's go ahead and divide that out. So I'm going to take my A, go back into that little formula box, and take A divided by D, which is 0.87. Okay, so now we can see that large, bold, we'll make this maybe blue. Okay, so now we have some nice dynamic text. So this would be perfect to give to kids to kind of explore this concept. So now as we change our angle around, we can compare sine and cosine values. The numbers make sense, I hope. I feel too, and I haven't done a whole lot of this in my class, but leading this kind of like this video discussion, let the kids build this too, because they're physically putting in values, which to me will make more sense of these trig ratios too. So now when we see that we have angles that are larger than 45 degrees, we can compare sine to cosine values and see that it's always going to be larger, right? And then if we're less than 45 degrees, we can see our cosine's a bigger value than sine and talk about why. We can also talk about at 0 degrees. We have a sine of 0, cosine of 1, help a little bit of our unit circle concepts. And when we have a 90 degrees, notice now with the hypotenuse being non-existent basically, we have some issues. Or that right triangle can't be formed. Can't have two 90-degree angles formed, right? So that's how we can create a nice little trig example and investigation tool for our students, and also using that dynamic text. So I hope that made sense, guys. Good luck with that.